To begin, a robot is deployed to known fire locations upon receiving a request, and in this video, the squares around each robot show the altitude-dependent field of view for each drone, and we also show simulated fires. The UAV first performs a feasibility test to ensure human safety guaranteed service. This feasibility test involves the UAV evaluating the probability that it can maintain a tight track on the fires under its purview, ensuring safe support of the human firefighters by not exceeding the track's residual bound, shown here in equation 1. The UAV infers the fire propagation model parameters in real time and evaluates this uncertainty residual ratio bound. Here, the UAV realizes that the uncertainty bound is not satisfied, meaning the UAV cannot guarantee that it can maintain a track on the fire. Therefore, a second UAV is recruited to cover the remainder of the path. Both UAVs will now perform feasibility tests over their assigned paths, each evaluating a separate uncertainty residual ratio bound. This process will continue until all uncertainty residual ratio bounds are satisfied and safety guaranteed service can be provided. This is shown in detail in the figure. Here, the second UAV has determined that it can perform fire monitoring without losing track of the uncertainty residual for the location and velocity of its fire front. However, based on fire propagation model parameters and dynamics, the first UAV has determined it may not be able to track the fire front, and so it calls in another UAV. The entire robot team can now guarantee online monitoring of the fire. Here we show the performance of our system on fires with moderate and aggressive growth rates. We see the team grows dynamically as necessary and is able to determine when it has safely established fire front tracking. Having learned the fire propagation dynamics, the UAVs collectively move with the fire front and seek to maintain high-quality information for the human firefighters using the uncertainty residual ratio bound. Meanwhile, unallocated UAVs can be used for distributed dynamic field coverage. Here we see unallocated UAVs being used for the distributed dynamic field coverage task. Each UAV observes and communicates information regarding the area within its field of view, again shown as squares around each robot. The areas they cover are determined by the UAV's uncertainty about the fire and are updated based on the learned fire propagation dynamics and parameters. The UAV team is capable of effectively covering the field area and maintaining high-quality information regarding the dynamic fire front.